All right, in the second video from this lecture, we're going to talk a little bit about how we can use the tool of regression. This is going to be somewhat associated with the first half of the lecture where we talked about causality, but we're mainly going to be focused on that, ruling out that first possibility for why two variables might be correlated, that there could be a coincidence. So we're largely going to be focused on thinking about how to establish statistical significance, which we've talked about before in this class, but we haven't necessarily talked about in the context of regression. Specifically, we've talked about using hypothesis tests when we have something like a t-test or an ANOVA or a chi-squared, and we've maybe alluded to using it in the context of regression, but we haven't gone through how to use those tools of statistical inference in a lot of detail when it comes to regression. So let's spend a little bit of time talking about that, because that is one of the tools that is used most frequently by economists and other social scientists when they're trying to establish causality. They'll often rely on regression and think about statistical inference in the context of regression. So at the top of this slide, you can see the regression equation. And this is going to look a little bit different maybe than the version of the regression equation that you saw earlier on in the semester. And that's because we now have this extra term at the end that is what we're going to call an error term or random noise. It's this little symbol that looks something like E. I believe it's eta, a Greek letter. And what that symbol is symbolizing is the fact that we're only going to get an estimate of whatever we are trying to study. Specifically, when we run a regression, we're only getting an estimate since there's some random noise in our model. In other words, we have some dependent variable we're measuring, maybe something like productivity. We have an independent variable, something like whether or not an organization has pay for performance. But whether or not an organization has pay for performance is not going to allow us to perfectly predict the value of our dependent variable, productivity. Instead, there's going to be other factors that also affect our dependent variable. This eta is going to stand in for all of those other factors that might be affecting the dependent variable. So that's what we mean when we write out this equation. When we are trying to do regression analysis and we're trying to do something like assess causality, often we refer to what we call the true model. In other words, we believe that there's some true relationship between the independent variable and the dependent variable. And we want to know what the true cause of, or what the true effect is. In other words, what is the causal effect that our independent variable pay for performance has on our dependent variable productivity? And we would say that B stands for whatever that true regression coefficient is. The best we can do, though, is to create an estimate of what that effect might be. And we're going to use hypothesis testing and confidence intervals to describe that estimate. Statisticians have spent a lot of time developing different formulas and helping people program statistical software to be able to say what those estimates should be based on, and specifically to get standard error estimates and coefficient estimates, which allow us to be able to conduct hypothesis tests and construct confidence intervals around our coefficient estimates. So for each coefficient that we get when we run a regression in Stata, it's going to show us a p-value, which we'll talk about more in the future, as well as a confidence interval. The p-value for that regression coefficient is going to let us decide if we can reliably conclude that the coefficient is non-zero. So this is very similar to what we've seen from p-values in the past. They're always allowing us to test a null hypothesis. And in the context of a regression, our null hypothesis is that the coefficient is equal to zero. So we're going to see from this p-value, can we reject that null hypothesis and conclude that the real effect of the independent variable must be something other than zero? If the slope is non-zero, then that means that x and y are related. So having a non-zero slope is just like having a non-zero correlation. It means that the two variables are related. But just because we get a positive correlation in our sample doesn't mean that there's a true correlation in the population. Or if we're making an estimate based on a regression, just because we see a positive coefficient in the regression doesn't always mean that there's going to be a true effect of the independent variable on the dependent variable, in part because we might have random noise. We almost certainly will have random noise, other factors that are also affecting our dependent variable. The hypothesis testing is going to help us consider, well, taking into account those other factors, that random noise, can we still conclude that our estimate tells us that the truth is non-zero? Again, there's always uncertainty whenever we have an estimate, but we want to know, even with that uncertainty, can we conclude that the true coefficient must be non-zero? Stata output is also going to give us a confidence interval for each regression coefficient. So that's an alternative way to think about the uncertainty around our estimate. So let's look at a quick example. We want to ask, does job tenure affect wages? And by job tenure, I mean how many years somebody has been working in their job. So let's look at a sample of women from 1988. I'm using this data set because it's one of the example data sets that Stata uses in their help manual. So it's very easy to load into Stata and to play around with. My dependent variable is going to be wages, which are measured in dollars per hour, and job tenure is going to be measured in years. So this is some language that I can type into Stata. And when I do that, I get output that looks like this. So you'll notice that I have a coefficient that comes out for tenure. And this coefficient, we've actually seen this earlier in the semester. If you've been doing the whole semester with me, this coefficient is telling us that for a 1 year increase in tenure, in other words, every additional year that someone works on the job, their wage is expected to go up by $0.19. In other words, 19 cents if we round. So we've learned how to interpret this coefficient. You'll see that right beside this coefficient, we have an estimate of the standard error of that coefficient. In other words, how precise is our estimate of that standard error, taking into account the random noise in the data set and the fact that we have a finite sample. We have about 2,000 observations. Beside that, we see a t-score, which is similar to what we get from a t-test, and we see a p-value. The p-value is what we need in order to be able to draw a conclusion about our null hypothesis that the real coefficient is equal to 0. And you can see that this p-value is very small. It's less than 0.05. And so we would say we can reject the null hypothesis that the true coefficient is equal to 0 and conclude that there is some real relationship between tenure and wage, even after taking into account random noise that is in our data set. You can also see that there's a confidence interval here. This is the lower bound of the confidence interval and the upper bound of the confidence interval. And you can see that that's what's being focused on in this first bullet point on the slide. So a rough interpretation of this would be that we're 95% confident that the true slope coefficient lies between 0.14 and 0.23. Notice that 0 is not contained within that range. So that's part of why we're able to conclude that there must be a non-zero relationship here. If we want to be able to put that maybe into more ordinary language, be able to interpret it, we could say something like, we're 95% sure that an additional year on the job typically corresponds to a raise that is within this range. It's going to be between another 14 and 23 cents an hour for 1 extra year on the job. That's what our confidence interval is telling us. It's not saying that that will happen for every person, because there's random noise that's going to affect each individual person. But that is what we can conclude the typical raise looks like after a year on the job. This slide is going to focus on that p-value that we already talked about. Like we said, we can reject the null hypothesis that the true value of the slope coefficient is 0. So in other words, after accounting for random noise in the data, we're confident that tenure is truly related to wages. In statistical language, we're often going to say that there's a statistically significant and positive relationship between tenure and wages. That's the way, if you're reading a social scientific paper, that they'll typically describe this relationship. Statistically significant and positive. All right. And that brings us to the end of this slideshow. So hopefully you feel more confident being able to think about causality when it comes to social scientific research. With this last example, we've mainly focused on what can we do through a regression framework to be able to rule out the possibility that we observe a correlation between two variables simply because of coincidence or because of random noise. And as you can see, these tools are pretty easy to use and will let you conclude that there is a relationship that isn't just due to coincidence. Of course, it's still possible that tenure and wage are related or correlated to one another because of one of those other possibilities that we saw in the first video. It could be that there's some third variable that's related to both tenure and wage. Maybe something like someone's education level is what actually drives their wage. And education level also happens to be related to how long someone has been working their job. And so maybe education is the real driver of wage rather than tenure. Or it could be that we have some sort of research design problem. Something like our sample is not a simple random sample, that we have a skewed data set where people who were further along in their tenure decided not to participate in our study unless they were a high wage earner. Maybe we have a bad reputation with whoever was collecting the data. And so people who had been around long enough to hear about our bad reputation didn't want to talk to us unless they could brag about how high their wages were or something like that. That would be an example of a research design problem that would cause a correlation that might not reflect a real causal relationship between X and Y. If we were to think about whether or not reverse causality could exist, that would be a little bit harder to imagine. We can't, it's not easy to think about if someone's wage changes, that's not going to change their amount of tenure. So we probably have to be less worried about that possibility. But we do have to think about, could there be some third variable that's causing this relationship, or could there be some sort of research design problem that's causing this relationship? If we're able to rule out both of those possibilities, we can probably conclude that there is some sort of causal relationship between tenure and wage, because we've already seen that this relationship is strong enough that it's larger than what we would expect from coincidence, because we rejected our null hypothesis that the slope is zero, and because our confidence interval doesn't include zero as a possibility. All right, that's it for today. I'll see you next week.